The next theorem is intermediate value theorem for integrals. This is Theorem 8, a very important theorem. Intermediate value theorem. Theorem for integrals. So the statement is, if f is mapping from a comma b and m comma n be infimum and supremums of f on a comma b, then they are asking us to prove that then m into b minus a is less than or equals to integral a to b f of x dx is less than or equals to capital M into b minus a. And also there exists a mu which belongs to small m comma capital M, that is closed interval of infimum and supremum, such that integral a to b f of x dx is equals to mu into b minus a. What is b minus a? The length of the rth subinterval. So what is that they are actually asking is, they gave f is mapping from a comma b and m and m are supremums and infimums on the function f of a comma b. And then this is a very important one. This is what we have to prove. And they gave mu belongs to m comma m. Okay, now we'll just look into the proof of the theorem. So what is that they gave? We have to first write down the given information. Given that f belongs to r over a comma b. What is r? Riemann integral. R over a comma b. Integral a to b bar f of x dx. Integral a to b bar f of x dx is equals to integral a bar to b f of x dx. Okay. Integral a to b bar f of x dx equals to integral a bar to b f of x dx. This is equals to the whole integral a to b f of x dx. This is a very important point. Just make sure that you remember this one. Next. After this one, let this be 1. Now, what is that they gave? Given that f is bounded on a comma b, and then we have to define a partition of closed interval a comma b, and then we'll take infimums and supremums. So what is that we have to write? Given that f is bounded, given that f is bounded on closed interval a comma b. Okay. And then we have to define a partition. What is that? P is equals to a equals to x naught, x1, so on up to xn, comma b. That be the partition on closed interval a comma b. Now we have took the function, we have defined the partition. Now what is that we have to take is infimum and supremum. So how will you take the infimum and supremum? Small m comma capital M be infimum supremum of f on a comma b. As these are infimums and supremums, we have to define it rth subinterval. So rth subinterval is given by IR is equals to xr minus 1 comma xr. And what is delta r? Delta is the length of it. Length of what? Length of the rth subinterval. Okay. Now, as we defined m and capital M for supremum and infimum and rth subinterval. So now we have to define MR, small mr and capital MR. That is at rth point or rth subinterval, the infimum is infimum and supremum of f where on the rth subinterval, that is IR. Now, what is the condition that we had earlier? M is less than or equals to, MR is less than or equals to, capital MR is less than or equals to capital M. For all R equals to 1 to so on up to N. Okay. Now multiplying delta R's. So you'll have M into delta R less than or equals to MR into delta R less than or equals to capital MR into delta R less than or equals to capital M into delta R. Now putting summation on all the sides. Summation R equals to 1 to N, M into delta R less than or equals to summation R equals to 1 to N, MR into delta R less than or equals to summation R equals to 1 to N, capital MR into delta R less than or equals to summation R equals to 1 to N, capital M into delta R. Now, as we have to take out this this M out, because there is no R over here, M into summation R equals to 1 to N delta R. This is less than or equals to, what is this? LPF, L into PF. This is UPF, UPF. This is less than or equals to capital M into summation delta R, R equals to 1 to N. We have done this process earlier also. So how can we write this? We can write this as M into B minus A. That is less than or equals to LPF. This is less than or equals to UPF. This is less than or equals to capital M into B minus A. Okay. Till here, like, let it be equation 1. What is that we actually have to prove? In places of LPF and UPF, we have to get the integrals. So we will just prove this one, LPFs and UPFs. Now make sure that you remember this one. This is equation 1. Okay. Now moving on to the next step, that is UPF. What is that we know from the earlier theorem? There was a theorem, UPF, one second. Yeah. UPF is greater than or equals to integral a to b bar f of x dx. This was the formula of the, when we defined UPF, we have wrote this one. And LPF is less than or equals to integral a bar to b f of x dx. Okay, and this we already know. Now I just wanted to write this as, what is that we know? We had one this thing, a to b bar f of x dx is equals to a bar to b is equals to integral a to b. So instead of a to b bar and a bar to b, I just wanted to write the whole integral, that is from a to b. So that is what we have to write over here. UPF is greater than or equals to the whole integral. What is that? A to b f of x dx. Okay. Same thing with LPF. LPF is less than or equals to the whole integral a to b f of x dx. Okay. Now, from these two, what is that we can conclude? You can write this as this one. If LPF is less than or equals to integral a to b f of x dx, write this one as integral a to b f of x dx is less than or equals to UPF. So from this and from this one, what is that you can conclude? You can write it as LPF is less than or equals to integral a to b f of x dx. What is integral a to b f of x dx? This. What is that? This is less than or equals to UPF. Am I clear till here? Let this be equation 3 or relation 3. Now substitute this one. Take this and substitute in 2. So what is that you'll get? You'll get m into b minus a is less than or equals to LPF less than or equals to integral a to b f of x dx. This is less than or equals to UPF, and this UPF is less than or equals to capital M into b minus a. Okay, so as these are less than or equals to, you can directly write small m into b minus a is less than or equals to integral a to b f of x dx. F of x dx. This is less than or equals to capital M into b minus a. Now till here, we got like m into b minus a and less than or equals to integral a to b f of x dx less than or equals to m into b minus a. This is finished. Now the second condition is they gave some mu. There exists some mu which belongs to m comma m, and they asked us to prove if integral a to b f of x dx is equals to mu into b minus a. This is what we have to prove now. So to prove this one, till here the first condition is finished. We have proved. Now what is that I wanted to take is to prove the second condition. I'm just taking this m, the small m is less than or equals to, what was the actual condition that we had? Like what was the last step? M into b minus a is less than or equals to integral f of x dx, that is less than or equals to capital M into b minus a. So what am I doing is this b minus a, I'm just sending that inside. So what is that? You'll get m is less than or equals to 1 by b minus a integral a to b f of x dx. That is less than or equals to capital M. Okay. So now I'm taking mu. I'm taking mu as 1 by b minus a integral f of x dx. I'm just defining mu as 1 by b minus a into integral f of x dx. So substitute this one over here. What is that you'll get? You'll get m is less than or equals to mu, which is less than or equals to capital M. So from this, what is that we can write? This mu belongs to small m comma capital M. As m is less than or equals to mu less than or equals to m, we can write mu belongs to small m comma capital M. Okay. So what is that we have at the last? Integral a to b f of x dx. Send this b minus a this side. What is that you'll have? Mu into b minus a. So this is what is the second condition. If there exists some mu, which belongs to m comma m, then we have to prove integral a to b f of x dx is equals to mu into b minus a. So there, we just took there exists some mu where it belongs to m comma m, then integral a to b f of x dx equals to mu into b minus a. This is a very, very important theorem. There are 99 chances to come. So make sure that you study this theorem properly. Next, there is a note point. That is a Doorbox condition. So what is that is? Darbox condition. So in this condition, what it actually says is that if there is an f, if there is a function f, which is a bounded function on closed interval a comma b. Okay. Then for all epsilon greater than 0, there exists some delta positive such that there are two conditions for that. What this condition says is UPF, that is upper Riemann integral or upper Riemann sum, is less than, UPF is strictly less than integral a to b bar f of x dx. Integral a to b bar f of x dx plus epsilon by 2. This is what the first condition is. And the second condition is LPF. LPF is greater than a bar to b f of x dx minus epsilon by 2 with norm p is less than delta. Norm p is less than, what is delta? The length. So this is what the Darbox condition says. Like you can make use of these conditions in any other theorems. So we will be using it in necessary and sufficient condition for integrability. Okay. Yeah. So the next theorem is necessary and sufficient condition. Sorry, I'll just write it in a short form. Necessary and sufficient condition for integrability. Either you can expect the previous question in the exam or this question because they both carry equal importance. Let us quickly move into the statement of the theorem. a bounded function f from a comma b to r, a bounded function f from a comma b to r, they gave it as a Riemann integral and on a comma b. So if and only if epsilon greater than 0, there exists a partition P of a comma b such that they are asking us to prove if 0 is less than or equals to UPF minus LPF is less than or equals to epsilon. So this is what we have to prove. Let us quickly look into the proof of this theorem. First, I'm taking the necessary condition. What is the necessary condition? If f belongs to a comma b to r, then we got to prove this. What is that? If f is mapping from a comma b to r, that is a comma b to the Riemann integral, then we have to show that for every epsilon greater than 0, there exists a partition P of AB such that 0 is less than or equals to UPF minus LPF is less than epsilon. So this is what we have to show. So to show this, what is that they gave? Given that f belongs to r over a comma b. Obviously, f belongs to r over a comma b. Then we have a condition. What is that? Integral a to b bar into f of x dx is equals to integral a bar to b f of x dx is equals to integral a to b f of x dx. So this is a condition that we have. Make a note of this by Doorbox condition. So what was a Doorbox condition? In Doorbox condition, what is that we have learned? We have learned if UPF is less than integral a to b bar f of x dx plus epsilon by 2. And what was LPF? LPF is greater than integral a bar to b f of x dx minus epsilon by 2. So these are the both conditions that we have learned. So from this one, what is that we can write from LPF? You can write minus LPF is less than minus integral a bar to b f of x dx minus integral a bar to b f of x dx. As we are multiplying with minus, this becomes plus epsilon by 2. Now see, from these both conditions, what is that we can conclude? From above relations, we can write UPF minus LPF is strictly less than a to b f of x dx. I'm just writing it like in place of this, I'm substituting this, and in place of integral a bar to b, I'm substituting this. So integral a to b f of x dx minus, I'm just adding this relation and this relation, minus integral a to b f of x dx, and you'll have like this is plus epsilon by 2 and this is plus epsilon by 2. So what is that? You'll have strictly plus epsilon. These both gets cancelled, so you'll be having UPF minus LPF is strictly less than epsilon. Okay, UPF minus LPF is less than epsilon. From 1, what is that we can conclude from 1? Like this two condition we got it from 1. So if UPF minus LPF is less than epsilon, we know that UPF is greater than or equals to LPF. We know this one. UPF is greater than or equals to LPF. If we write this UPF minus LPF, this will be greater than or equals to 0. And what is that we got? UPF minus LPF is less than 0. UPF minus LPF is greater than 0. So we can conclude that 0 is less than or equals to UPF minus LPF is less than epsilon. So this is what the first condition is. See, we have to prove this one. We've proved this one. Now moving on to the sufficient condition. So what does a sufficient condition tell? We have to take this condition. For all epsilon greater than 0, there exists a partition AB such that 0 is less than or equals to UPF is less than or equals to LPF. Sorry, this is minus. UPF is less than or equals to UPF minus LPF. This is less than epsilon. Then we have to show that f belongs to r over a comma b. We have to just take this one and prove this one. So how will we prove? And we already know that we have proved this condition in case 1. Okay, and write this one as given that UPF minus LPF is less than epsilon. Take this as equation or relation 2. Now, UPF, what is UPF? UPF is greater than or equals to integral a to b bar f of x dx. This also we know. What is LPF? LPF is less than or equals to integral a bar to b f of x dx. This also we know. Now for LPF, just put minus on both sides. LPF is greater than or equals to minus integral a bar to b f of x dx. Okay. So from these two relations, what is that we can write? We can write it as integral a to b bar f of x dx minus integral a to b a bar to b f of x dx is less than or equals to UPF minus LPF. Okay, from these two relations I got this step. So what is UPF minus LPF? This is less than epsilon, right? This is less than epsilon. And integral a to b bar minus integral a to b bar, we can write it as a, like put this one as a to b. So in the next step, write integral a to b bar f of x dx is greater than or equals to integral a bar to b f of x dx. This is from a known result. So if these both are greater than or equals to, what is that we can write? Integral a to b bar f of x dx minus integral a bar to b f of x dx is greater than or equals to 0, right? And what is that we got? Integral a to b bar, a to b bar minus a bar to b is less than 0. So from these two conditions, what is that we can write? 0 is less than or equals to integral a to b bar f of x dx minus integral a bar to b f of x dx is strictly less than epsilon. You can write this right? So make sure that you remember this step. What is that? 0 is less than or equals to a to b bar minus a bar to b f of x dx is less than epsilon. Now just we know that, what is that we know? Epsilon is greater than 0. Obviously epsilon is the least positive integer. I'm just taking minus epsilon. Minus epsilon will be less than 0 because it is a negative number. So instead of 0, I'm just putting minus epsilon. What was the condition that we got in the previous slide? 0 less than or equals to integral a to b bar minus integral a bar to b f of x dx is less than epsilon. This is what we got, right? So instead of 0, I'm just putting minus epsilon. Minus epsilon is less than 0, which is less than or equals to integral a to b bar f of x dx minus integral a bar to b f of x dx, that is less than epsilon, right? So from this, what is that we can conclude? Integral a to b bar f of x dx is equals to integral a bar to b f of x dx. So that therefore, what is this? F belongs to R over a comma b. How did we get this step? Because the integrals are lying between minus epsilon to epsilon. So if you put that in an equality form, this will be a to b bar f of x dx is equals to a bar to b f of x dx. Okay. After this, yeah, we'll just end this session over here.